Swayam Prabha. Digital India. Educated India.
Welcome back, and I have now some continuation of discussion, and this is with stochastic conditions. Yeah, so the system with stochastic conditions, because I told you that in the ambient conditions we could have variable frequency, and however, in our laboratory or some studies, like numerical studies, it is difficult to repeat some variable conditions, and we can do some two limits. This is the most important limits, but we can assume that we have harmonic excitation like it was before, or we can have stochastic bifurcation, or maybe we have both. This is like harmonic with some added noise. So this is like a stochastic component. So in this presentation, I want to describe some of the influences of a noise. The first is very simple, and the first point, and I think that this point is the most important for us. There is like a stochastic excitation, and we are using white noise. If we are using white noise, so white noise is the very simple, realization of noise, and I would tell you why. Because if we have harmonic excitation or harmonic signal, then we have one frequency. But if we have a white noise signal, then we have all frequencies equally distributed. So this is the extreme effect. We also did some continuation of such study with added noise, but we have both stochastic and harmonic. However, this extension is useful for nonlinear systems. Because in nonlinear systems you have multiple solutions, and some solutions would be more stable and in the presence in noise. So this is the obvious expectation, because you have if you add some noise and you already have you already have some harmonic excitation, but you can imagine that you have complicated potential, but you have two minima and the barrier in the potential. Then you could have not enough energy to pass through the barrier. And if you add a little bit more noise, you add also energy to the system, and you can easier pass. So you can find some useful solution for us, large amplitude solution, which could be induced by some additional noise. But this is the study for nonlinear system. So I would like to start from the linear. Here, I just want to revise that what is the aim of our study. Our study is related to some small device, and the small device which could be used to power some small electronics, or you have sensors. So in some body you can have sensors, or you can have some structural health monitoring, like breach, for example, and you want to have self-powered sensors, but they don't need some additional batteries, or you have battery, but you want to recharge this battery in continuous way. in continuous way, it would be recharged, and when this is the very useful application. And when I was on the conference in Lyon, there was a colleague from US, and he told such a story that, for example, you can imagine that there is somebody and he had a problem with a heart, so this is like a pacemaker. Pacemaker is not working because battery, so immediately stopped. But you can extend the battery life in some way if you have continuous charging of a battery. So this is during your motion you can charge, and here you can imagine some shoes with bistable elements. So this is like a PZT, but these are bistable, just to have two different mod shapes which could be switched during walking. So the switching between two modes is quite two stable positions is quite interesting approach to the nonlinear systems also. And now I would like to tell that the piezoelectrics and piezoelectric devices were suggested to be good transducers in the beginning of 2000 years, but people realized that these devices are maybe working only for single frequency, so they are not very useful, but we are still talking about that. Tomorrow there would be another lecture about nonlinear effects, so I would leave this for tomorrow. But now I just want to discuss some results, and not all results, but from our paper with a colleague from Swansea, colleagues from Swansea. So Sandeep Hikari, Mike Friswell, and Koda Parast, Hamid Haddad in Swansea. And this was so in this paper we also investigated such a system, the original system with a resistor and also with an inductor. Yeah, so there is additional one. And here I want to just to focus on the first solution without any change in electronics, because this would be maybe left for the last future. This is like advanced development and some future perspective, which is on the last maybe one before last day. So this would be left on that. Some information and ideas for the electronics. However, here I told you that there could be some additional frequency by this coil. So you have a capacitor which is inside the piezoelectric layers, and this is capacitor is outside, yeah, but this is in that part of a structure, and then you have only the resistor, the load resistor, and the tip mass is because you need some change of the shape. So there is some change of the shape in that system, and now there is one more comment about the shapes of electrodes. There is also a question about the shape of a beam. The shape of a beam can be also modified, but also the shape of electrodes. And the problem with the electrode is that it has not the the deformation is not happening in all the points in the same way. Yeah, but you know, there is another point with a voltage on the electrodes. If you have the voltage on the electrodes, you have the same voltage just in all these distances, because it would be just connected electrically. The electrode, which is along the beam, is connected electrically, and the beam could have some tendency to be deflected, to have the same curvature in each point, and this is some drawback of this. Of such a solution, but we cover the electrode on the whole beam. So usually people are preparing such a design that you have the electrodes only, or maybe even the piezoelectric itself, because this is like active part of piezoelectric would be only covered by electrode. So you have that part which has the large deflection. Is covered by piezoelectric and electrode. Yeah, so this is the one of the interesting points. But if you look to the laboratory, then the beam is not covered in the total length, but in this point, in this short interval where you have the largest deflection. So this is the interesting point. And here we studied the stochastic excitation in this research. The stochastic, and when you remember the equation. It is the same equation. However, this FB is a stochastic. Excitation. It's a stochastic excitation. So in vector notation, you can write such. The equation could be written. You decouple the second order to the first order equation, and you can tell that there is a velocity, there is a displacement velocity and voltage. In our case, and we can look for the matrices. So there are some matrix. It's a vector here, and this is additional matrix. If you decouple, then you can write in a matrix form. Because here I wanted to show you what is going on if we perform a Fourier transform or Laplace transform for imaginary domain. The domain of the Laplace domain would be like I times omega, the omega frequency. I want to show you what would be that how this equation could be transformed by the Laplace or Fourier transform, and maybe then afterwards we can predict what is the power output. In the paper we did some more because but I was thinking that this is maybe too advanced because we also did some statistics of extreme values, voltage extreme values. So the statistics of extreme values would be helpful to optimize the resistor in that system, and this is our aim in the paper, but this is like a nice discussion about how to solve a linear system with noise, because this is linear system, and in our paper, the most important was this development of this extreme values or voltage or maybe peaks of voltage statistics. So you have you see that this is the random process, and if you calculate you can calculate the autocorrelation function. It is like a Dirac delta. Dirac delta is multiplied by some strength of a random process. So this Dirac delta, if you calculate Fourier or Laplace transform, you have one. You have one from Dirac delta, and this is some simplification to the system, because in the time domain it is complicated because you know that this is the random process, so you can tell that this is the number, the even infinite number, because this is like a academic example. In reality, you have some band of a frequency, but in Gaussian noise, you can tell that there are some tails, and you have these tails are just responsible to have the total representation of all the frequencies. So this is all the frequencies are represented in the same with the same weight. So you have after the Fourier transformation of this delta, you have one, or Laplace transformation, and here you have the equation. You have the equation. This is the equation for the even if it is you can also observe that this transformation is working on also for squares, for the higher orders of derivatives. No, not squares, but higher order derivatives. Like second order derivative is giving you omega square. So this vector representation could be reduced, but you can get such algebraic equation. So the advantage of transforming linear equations to the frequency domain is that we reduce the problem to algebraic equation. But we are not solving now. This is the derivatives, but differential equations. But we are solving only algebraic equations. The drawback is that we have also imaginary parts, like I is like a imaginary number. Yeah. So this is coming here because this is the simplest way. You know that in half an hour or maybe an hour ago, I just solved the system postulating some solutions, and I did this with sinus and cosine, but the exponential function, which is which it has also some decoupling to sinus and cosine. So this is. This could be like imaginary exponential function, could have sinus and cosine inside, and for the nonlinear system you cannot do this because you can have some multiplication of the terms where you have I, but here you can easily distinguish the imaginary and real parts, and this is like it is similar to distinguishing between the coefficients between which are staying in front of a sinus and cosine, and here you have decoupling to the imaginary and real numbers. So you have you can tell that this could be imaginary part, could be just collected terms with the imaginary numbers, and the terms with real numbers could be just also selected. And this delta is also given here. Yeah, so the determinant. and when it is possible from this after this transformation, it is simple to estimate the power output. The actual power output would be voltage square divided by resistivity, because this is piezoelectric system, and you have some average because you are interested in some average. So the average can be estimated, and this is like a noise level is this S0 of our stochastic excitation, and the rest is coming from the matrix manipulation. And of course, the result is a real number. However, on the way, you have to look carefully, because there are some imaginary parts and real parts. But of course, you are interested in square, and this is like a variance. So variance. Oh, this should be square here. Yeah. So sorry, because this is my mistake. Yeah. So I would tell that this is the main result for stochastic, linear system power, and this could be also derived analytically. This can be also calculated in the numerical way, but the problem with some numerical calculations is that you have by linear system you cannot change frequencies. Yeah, so you have input and output, and you usually, if you have some input, then output is proportional to the input, and it is even easier to observe for the after the Laplace transformation, but this is the case. So I would tell that this is the main result, but this could be very simple, simply estimated. However, in nonlinear system, the frequency can be changed. So not only the proportionality is changed to some other rule, but also the frequency is changed. So, for example, the simplest observation in nonlinear system is that you have so-called subharmonics and superharmonics. Yeah, so the subharmonics and superharmonics are coming as the multiple frequencies. So you have frequency omega, but you have, if you have in the input frequency omega, in the output you can find also double omega, 3 omega, and multiple omega, and also fractions like half omega and 1/3 of omega and 1/4 of omega, and so on. So these are one of the advantages in the nonlinear system, that you have you change the frequency. So this is it is the frequency of a solution. In our case. So I'm approaching to the end of the presentation, because the next I want to I want to discuss in the details tomorrow, but this was broadband vibration energy harvesting, and I would tell that the broadband energy harvesting started from that paper, Erturk, Hoffman, and Inman in 2009. I told you that piezoelectrics were studied, for energy harvesting, studied even in early 2000 years, like 2003 and maybe 2001. However, people realized that this is only single frequency, and by changing of frequency from input to output, you can imagine that you have more freedom, and this would be easier adjusted for variable conditions if you have more frequencies available than just only the natural frequency. So for nonlinear system, there are some other features, more resonances and more solutions, and also the change in the frequency between the input and output signals. Yeah. So this is the robust effect. Yeah. Yeah. So I think that we should stop now. Yeah. Yeah, so because these were 2 hours planned for today. Yeah, harmonic excitation, and I would show you how double well was designed. So the double well was designed by some additional magnets. You have a beam like previous time, but the vertical position of a beam is not stable anymore because the beam is ferromagnetic, and here you have some additional magnets which are attracting the beam to one or the second position. So 2 positions are stable, and this group in 2009, this is American group, so they found that the level of response, this is like a voltage, root mean square voltage, it's much better for a nonlinear system comparing to the linear one. So the linear one is with this peak, but you can see that also for the smaller frequencies you have better response. This was not commented so much because they were not interested in such a complete explanation, but it was modeled by the simulations. The model was provided and confirmed or validated by experiment. It was a good result, but it was like a short paper informing that there is such a possibility to have broadband, and the broadband, you see that it is broadband is also in the title of this paper. This is like a piezoelectric structure for broadband vibration energy harvesting, and later this effect was explained by some other people, but also in the same year, 2009, there was another group, Italian group. This is Francesco Cotone, Elias Bocca, and Luca Gamaitoni from Italy. Yeah, so they published also short paper, because letters is usually the short paper, and they titled the paper "Nonlinear Energy Harvesting." And this nonlinear energy harvesting was different. It was different paper than the previous one, because the previous was harmonic excitation, and this one paper was with stochastic excitation. Yeah. So this is interesting that both directions were used, and excitation of that system was a little bit more advanced. So they had some electromagnetic exciter. So this is actuator, electromagnetic actuator with coils, additional coils, and they put some repulsive magnets just to destabilize the vertical position. So this was similar. However, the realization was different, and they specially used these electrical actuators because they wanted to provide the stochastic force. So it is easier to just to not to shake the whole system, but to provide some electrical signal to change the motion. So the force was stochastic. The force was stochastic here. So this is like an input was stochastic excitation, and in the previous paper they used harmonic excitations. Yeah, you see the harmonic excitation you see here. This is like a shaking with some cosine omega t. Yeah. So in that results you can see that it was like a sweep of the frequencies. This acceleration is keep constant for different frequencies, but when the output, this is voltage output, is coming is going up and down for the linear system, informing about the resonance region. Yeah, so this is the original finding, and in that paper, Italian, it was more difficult, but you can see that they discussed some potential, which is made. You calculate potential by choosing some generalized variables. So this is the distance which is measured here, the x. In the laser, yeah, you can also measure by the laser, but you can estimate some deflection by the x. So that distance you can use x as a generalized coordinate, and then you can see that if just looking for large distance, yeah. So with like a large distance, I have this arrow here. Yeah. So if you look for the large delta, the large delta means that one curve. So this is like a parabol. The large delta is this parabol. So this is linear system. If you have a large distance of in delta, this this magnetic interaction is decaying fastly. Yeah. So only if it is very close, if the interaction is strong. But you can see that this is almost like no interaction if delta is 15 millimeters. But if it is shorter distance, when interaction is stronger, and you observe some at first some kind of flattening of a potential, and then it's like a barrier. But finally, it is not easy to move through the to stay, or maybe to stay in vertical position, and in other words, the beam is buckled. Yeah. So you have buckling on the left or buckling on the right. On the right and on the left, yeah. So you have two stable or static equilibrium or shape equilibrium. This is deflected to the negative x and to positive x. Yeah. So this is and if you have some small oscillation, because now you think what is the excitation doing, because there is no we are not talking about resonance. However, we can tell that if we have some distribution of frequencies, so this is like all the frequencies are covered, and there could be some interaction with a natural frequency, but it is a small component. You need more energy just to go through the potential barrier, and by adding higher, more intensive noise, you increase the energy in the system.